Hello, everyone. Today, I'd like to introduce Ameba's HMI Smart Display Solution, a graphical interface solution for embedded systems. First, let me outline the agenda. The talk is in 4 parts. Part 1 is an overview, the solution as a whole, the chip lineup, and application scenarios. Part 2 is the Ameba HMI full-stack solution, which covers the software side. Part 3 is the Ameba hardware engines, using measured data to show what the PPE, JPEG, and LCDC can do. The final part is a summary, along with how to get started right away. Let's begin with a high-level view of the solution. The Ameba HMI comes down to a single idea: one display, opening up multi-dimensional interaction. It delivers completeness on 3 levels. First, every scenario. From smart home control panels and color displays on major appliances, to patient monitors, industrial PLCs, and children's learning devices, all are real-world use cases. Second, the complete chip family. The lineup spans from small SPI displays all the way to MIPI-DSI flagships. In other words, from electronic shelf labels to robot HMIs. Third, a full software stack. Full stack support from chip to system to cloud, with operating system coverage spanning FreeRTOS, Zephyr, and Linux. In short, this solution helps brands build competitive, user-friendly smart devices. Let's start with the chips. A range of ICs covers every display need, from cost-optimized small SPI displays to MIPI-DSI flagships that run Linux on dual cores. Specifically, the entry-level uses an SPI interface with a 320 by 240 display. The flagship uses MIPI-DSI at 1024 by 600 with a built-in dual-core Cortex-A32. A single product line spans the full range, from entry-level to top performance. Choosing an interface is essentially about balancing cost, power, and performance. We offer 3 technical paths. The first is SPI and QSPI, built for maximum cost efficiency. It uses very few signal lines, cutting PCB complexity considerably. Its low power suits battery-powered designs, and the GPIOs it frees up can go to sensors and other peripherals. The representative models are the RTL8713E and RTL8721DX. The second is RGB, emphasizing high integration and efficiency. This path integrates 3 engines on chip, the LCDC, PPE, and MJPEG. Drivers are mature, development cycles are short, and it's easy to mass produce. It supports 800 by 480 and high refresh rates. The representative model is the RTL8721F. It uses 2 lanes at 1 gigabit per second each, supporting up to 1024 by 600. Differential signaling gives strong noise immunity, and paired with a 1.2 gigahertz dual-core Cortex-A32, it can run complex applications on Linux. The representative model is the RTL8730E. In summary, choose SPI-QSPI when cost comes first, RGB for a balanced design, and MIPI-DSI when performance is paramount. The Ameba HMI is a full-stack solution, 5 layers, all sharing a single SDK. The top layer connects to the cloud, providing OTA, device management, and data services. Below it is the application layer, which handles the UI, interaction logic, business features, and multi-screen navigation. Next is the GUI middleware, built around our deeply ported LVGL, complemented by imaging, font, and persistence services. Below that is the OS layer, supporting FreeRTOS, Zephyr, and Linux. The bottom layer is the driver and hardware adaptation layer, which interfaces with the display, PPE, JPEG, LCDC, touch, and other low-level hardware. The key to this architecture: all platform-specific code is consolidated in the bottom layer. A single initialization entry point brings up the display, hardware, and file system together, while screen parameters are managed centrally in one registry. The direct benefit: when you switch chips or displays, the application code stays untouched. Because neither a new display nor a new chip requires code changes, one UI project can cover screens and scenarios of all shapes and sizes. For example, patient monitors, PLCs, and robot HMIs in medical and industrial fields, and a smart home hub where one display controls lighting, air conditioning, and security throughout the home. color panels on major appliances, refrigerators, ovens, and washing machines, and, in consumer and education settings, smart speaker displays, e-bike dashboards, and children's learning devices. Different forms, sizes, and interfaces, yet the same UI project runs behind them all. Now for part 2, the software side. How one UI project runs across the entire chip family. This builds on a complete SDK, a deeply ported LVGL, and support for multiple operating systems. Many solutions in the industry claim to support LVGL, but between it runs and it runs fast lies a crucial layer of work. Our approach, starting from open source LVGL, we add the layer that ties it tightly to the chip hardware. Take the RTL8721F as an example. This layer adds 4 capabilities. First, hardware accelerated rendering. Operations such as fill, scaling, rotation, and layer compositing are handed to the chip's built-in 2D graphics engine, the PPE. Handled in hardware with little CPU involvement, scrolling and animation become noticeably smoother. Second, automatic hardware image decoding. JPEG images are decoded directly by the chip's built-in MJPEG hardware decoder and sent to the display, fast, and with almost no CPU load. Third, double buffering with frame synchronization. 2 frame buffers alternate, swapping whole frames in sync with the display refresh. A stable image with no tearing and no dropped frames. Fourth, minimal initialization. A single entry point brings up the entire graphics environment. The application never has to set up the display, buffers, or drivers itself. Beyond graphics, the solution includes a set of common application layer capabilities, letting developers focus on their product's interface and features. There are 3 main parts. First, screen management. The app is organized into screens, and the solution manages the transitions and back navigation between them. Built-in transitions include fade and slide, and showing, hiding, and reclaiming screens is all automatic. Developers handle only the screen content. Second, parameter storage. Parameters such as device settings and runtime state can be stored persistently, surviving power loss and reboots. Common types, switches, values, and text can be read and written directly, and the underlying file and flash storage is handled for you. Third, image display. It supports common formats such as JPEG, PNG, and BMP, detects the format automatically, and can scale or crop images before display, with no need to port decoding libraries or handle format adaptation yourself. All 3 are built-in and ready to use. Next is a key design element, hardware-software collaboration. Its goal is to ensure that the same UI project migrates across chips of different tiers with 0 changes. The premise is practical. Chips with accelerators take the hardware-accelerated path with the PPE, JPEG, and LCDC fully engaged. Chips without accelerators take the software-optimized path, where deep optimization keeps the UI smooth. So how does it decide at runtime? For every rendering task, the system first checks whether the hardware engine can handle it. If it can, the task goes to the hardware engine. If not, it automatically falls back to CPU-based software rendering. The entire process is transparent to the application above. A note on chip selection. Not every Ameba integrates all the acceleration engines, but every one runs LVGL smoothly. Back to the question of swapping displays. In this solution, parameters such as resolution, color depth, and refresh rate are all managed by a configuration layer. It works in 3 steps. First, a unified interface. Each display is described by a single parameter set: resolution, timing, color format, and initialization sequence. RGB, MIPI, and SPI are all managed the same way. Second, table-based matching. At runtime, the system matches the display by resolution against a screen registry and supports the nearest compatible substitute. Third, presets for mainstream displays. Common display drivers are preloaded and ready to use. Switching to a supported display takes 1 config change. Adding a new one takes just 1 more parameter set. Several display drivers are already supported, such as the ST7701S and T1720A. Different chips support different interfaces. RGB on the RTL8721F, MIPI-DSI on the RTL8730E, and SPI on the RTL8713E and RTL8720E. To close the software section, Let's look at the accompanying demos. We provide a full set of production-grade demos with fully open-source code and a graphical configuration menu. Run them with a single click, ideal for learning and reference. For example, widgets, showing interaction across more than 30 controls. Smart Hub, a smart control panel. E-bike, a two-wheeler dashboard. And coffee machine, showcasing animations and lists. That covered the software side. Now for part 3, focusing on the hardware. The 3 engines, the PPE, JPEG, and LCDC, that are the foundation of consistently smooth UI. First, MJPEG hardware decoding. It consists of a JPEG decoder and a post-processing unit, which can work independently or together. From decoding, rotation, scaling, and color conversion to overlay output, everything is done in hardware with almost no CPU involvement. As shown in this pipeline, the JPEG bitstream comes in, is decoded in hardware, and produces intermediate YCBCR data that never touches DRAM. It goes straight into the post-processing unit, which handles scaling, rotation, color conversion, and alpha blending, and finally outputs display-ready RGB for the LCDC. The key here is that the intermediate data never touches DRM. The decoder and post-processor form a single pipeline, so the YCBCR data isn't staged in memory, saving one large DRAM write and one read. This means lower power, shorter latency, and near-zero CPU load for IoT MCUs where bandwidth is already tight. It's also highly flexible with formats. Inputs cover every YCBCR subsampling format: 400, 411, 420, 422, 440, and 444. Outputs can be configured as ARGB 8888, RGB 5C5, or ARGB 4444. This slide uses measured data to show what hardware decoding delivers. The test platform is the RTL8721F. The baseline is lib-lep-jpeg turbo with SIMD optimization enabled. The conditions are 800 by 480 direct display, averaged over multiple iterations. The result, roughly 10 faster on average, and up to 12 for the most common 420 format. In terms of time, with PSRAM, hardware decoding stays under 16.6 milliseconds across all formats. 16.6 milliseconds is an important threshold. It's exactly the duration of a single frame at 60 frames per second. In other words, hardware decoding keeps every format comfortably within the 60 frames per second budget, so both video and animation run smoothly. Next is the PPE, the Pixel Processing Engine. It's a lightweight 2D pixel processing engine that uses dedicated hardware to accelerate format conversion, geometric transforms, multi-layer blending, and color keying on raster images, reducing CPU load effectively. One engine, 5 capabilities. Color space conversion, with hardware conversion between formats such as RGB 565 and ARGB 8888. High-quality scaling, using bilinear interpolation to fit various resolutions. Rotation at 90, 180, and 270 degrees, alpha blending with semi-transparent masks and up to 3 layers, and color keying, which makes a chosen color transparent with an adjustable transparency range for easy compositing. Here are some measured hardware results, all at 800 by 480, RGB 565, single frame. Alpha blending of 2 semi-transparent layers, 7.45 milliseconds, a full-screen 90-degree rotation, 5.92 milliseconds, and, for a live wallpaper scene with PSRM and tile rendering optimization, the frame rate rises from 19 to 38 frames per second. Offloading these highly repetitive computations to the PPE frees up the CPU. The third engine is the LCDC, the display controller. This on-chip controller is highly configurable, with a built-in pixel format converter that adapts to a wide range of display panels and resolutions readily. Its role in the chain is the final link, from the image in memory to the lit-up screen. As shown, once LVGL has drawn a UI frame into the frame buffer, the LCDC reads it automatically via DMA and performs pixel format conversion, then outputs it to the panel according to each display's own interface and timing. The outputs of the PPE and MJPEG are written to the frame buffer first, then sent out by the LCDC similarly. As for its 4 capabilities, first, a built-in PFC pixel format converter done entirely in hardware with no CPU load. Second, multi-interface output supporting RGB parallel and 8080 interfaces. Third, highly programmable timing that precisely matches the specs of different panel makers. And fourth, a rich set of pixel formats with native support for RGB 565 and RGB 888 and output bit widths of 6, 8, 16, and 24 bits. It's the foundation for driving a wide range of panels with flexibility. With the capabilities now laid out, let's wrap up with a summary and how to get started right away. Looking back over the talk, the benefits of this solution come down to a few points. JPEG hardware decoding delivers a 10/12 speedup. In the live wallpaper scene, the PPE doubles the frame rate. A single SDK supports more than 5 ICs, keeping migration costs low, and for interfaces, you can choose from QSPI, RGB, and IP. Even on chips without accelerators, software takes over and the UI stays smooth. And the solution as a whole connects the full stack, from chip to operating system to middleware to cloud. If you'd like to start developing, the first resource is the complete SDK. Download it and use it out of the box. The address is github.com. Ameba IoT, Ameba at FreeRTOS. The second resource is comprehensive online documentation. The HMI development guide is published on AIoT realmcu.com. The address is AIoT realmcu.com en latest. From download to first use, the documentation guides you through every step. That concludes today's presentation. Ameba HMI is dedicated to helping every display run at the speed it deserves. Thank you for your attention.